Good day, everyone. Today, I'll be presenting my findings for Laboratory Activity 6, which focus on the concept of odd symmetry in digital signals. The primary objectives for this lab were to successfully generate signals with odd symmetry using Python and to verify this property both visually through plots and numerically. A signal x of n is defined as having odd symmetry if it satisfies the mathematical condition x of negative n is equal to negative x of n. In practical terms, this means the signal is antisymmetric, which respect to the vertical axis. If you flip the signal horizontally, or time reversal, and then flip it vertically, or amplitude inversion, you get the original signal. This property is particularly useful in areas like signal analysis and Fourier decomposition. For this activity, we use Python with NumPy and Matplotlib. First is signal generation. We generated a time axis n from negative 10 to 10 when we then created two examples of odd symmetric signals, a discrete sine wave x sub 1 of n is equal to sine 0.3 pi n, a cubic function x sub 2 of n is equal to n cubed. We then plotted both the sine wave and the cubic function clearly showed the odd symmetry. The plot is mirrored and inverted about the origin. Numerical verification. To confirm the property programmatically, we use the NP flip function to create the time reverse version of each signal, x of negative n. We then check if this reverse signal was equal to the negative of the original signal, negative x of n, using np.allClose. Both checks return the expected output true. This confirms that the generated sine and cubic signals strictly adhere to the mathematical condition for odd symmetry. Let's briefly summarize the key concepts from the analysis portion. Number 1. Odd versus even symmetry. The key difference is the axis of symmetry. Even symmetry is a simple mirror image about the vertical axis x of negative n is equal to x of n. Odd symmetry is antisymmetric about the origin, requiring both a flip and an inversion. Number 2. Fourier series implication. Signals with odd symmetry contain only sine terms in their Fourier series expansion. This is because sine functions are naturally odd functions, while cosine functions are even functions, including cosine terms would violate the required x of negative n is equal to negative x of n condition. Real-world application. A great real-world example is the current waveform in an AC power system. The positive half cycle is the negative of the negative half cycle. This odd symmetric property is crucial because it ensures the signal's average value is zero, which is essential for efficient AC power transmission. In conclusion, this laboratory activity successfully demonstrated the generation and verification of odd symmetric digital signals, highlighting how this fundamental property dictates a signal's behavior and composition in areas like Fourier analysis and real-world electrical systems. Thank you.